In our previous discussion of Aldol reactions, we only talked about reactions taking place between two molecules of the same aldehyde or ketone. But we can also look at crossed Aldol reactions, which are also known as Claisen-Schmidt reactions. And in the case of these reactions, now we're using two different carbonyls. So one will act as a nucleophile, one as the electrophile. So let's consider a case where we use two different ketones. We have ethyl methyl ketone, and then we'll say, what if it reacts with ethyl isopropyl ketone? Conditions will be the same, base and water. In the case of this reaction, if you look, there are 1, 2, 3, 4 enolizable positions. That means we can form 4 different nucleophilic enolates, which can react with each of the carbonyls. So you're going to have 4 or potentially even 8 different products. Because you can consider the enolate from this position attacking this carbonyl or attacking itself. The enolate from this position attacking this carbonyl or attacking another molecule of itself. So this ends up being a complete mess. So crossed Aldol reactions like this are really completely useless. But we want to think about some ways we could actually make this reaction useful. Because you can imagine synthetically, it could be quite useful to be able to react two different carbonyls together. So there's a few different strategies we can use that makes this reaction work well. First is, what if we use one carbonyl that doesn't have any alpha hydrogens? So what that means, let's say you have benzaldehyde. This has no alpha hydrogens, which means it's the de facto electrophile. It can't act as a nucleophile. And maybe we'll react this with acetone, which is also a good choice because it's a symmetric carbonyl compound, meaning it only has one type of enolizable position. So now if you react these under our conditions of base and water, we can draw the enolate we'll get, and that's the enolate of acetone. That will attack our electrophilic carbonyl. And once that gets protonated, that O minus becomes an OH. So we get this beta hydroxyketone, and then in the presence of the base, this will lose water. So if you want to draw in one of the hydrogen here, we lose H and OH across that alpha beta bond. To get our final product. There's a second way that you can make the crossed Aldol reaction useful by forcing one of your carbonyls to be the nucleophile and one to be the electrophile, and that's to use one that is especially acidic. Now let's say we're reacting acetone and this 1,3-diketone. Between these, if you think back to our discussion of acidity, both have alpha protons. I'll just draw in a CH3 on this one, but the pKs are vastly different. The pK of the alpha protons on acetone is around 20, while the pK of these alpha protons between the two carbonyls is about half that, at 9. So because that's the most acidic position, the enolate will form here. That means this will be our nucleophile, this will be our electrophile. So if we subject this to base, we're going to form the enolate, the dicarbonyl compound. And I'm going to just draw a simple resonance structure where the negative charge is on the carbon. Now we can react that with the acetone electrophile. I'll put it in a different color just to help us keep track. So we attack there. Here's our new bond. There's O minus, and the acetone has the two methyl groups. So let's just finish up walking through the mechanism to get to the product. So the next step, we'll get a proton from the water. And then from there, we need to do the elimination. That involves using a base. So that base will take the alpha proton and again, I'm not taking any shortcuts this time, drawing out all the steps. This will be if you're asked to draw the full mechanism. So now we get the negative charge here, and then that will come down and we'll eliminate the hydroxide. So if you want to draw your byproducts, We lose hydroxide in this step. Over in this step, we would have lost water. But the net result, because you put a hydroxide in, the net result is you lost H and OH from the molecule. So a dehydration step there. There's one final way we're going to look at to make the crossed Aldol reaction useful. And this might be the most common method to do this in a lab. So what we do is, instead of using a weak base like hydroxide where you have an equilibrium, we use LDA as a base to form 100% of the enolate of one carbonyl compound. Once we do that, then we slowly add the second carbonyl compound. So let's say, for example, I want to react cyclopentanone and acetaldehyde. And specifically, I want cyclopentanone as the nucleophile, acetaldehyde as the electrophile. So just reacting these under base would probably give you a mess. In fact, the aldehyde's a little bit more acidic than the ketone, so this even has a higher likelihood of being the nucleophile. So if you want this specific set of conditions, what we can do instead, we'll start and just put your preferred nucleophile in your reaction flask. So we would probably put that in a flask with THF as a solvent and add LDA to that. So you may not always see the THF written in as a solvent, but if you do, that's what it is. LDA, THF, and this is done at a low temperature. And we've used LDA before to form enolates. So what that does is the base takes the alpha proton and gives us the enolate. Again, I'm drawing the minor resonance contributor just to make it a little simpler. But the thing about LDA is because it's such a strong base, there's no equilibrium here. We're forming 100% enolate. Now that you have that formed and stirring in your reaction flask, we can take the acetaldehyde and add that slowly. And the slow addition helps this nucleophilic attack occur as opposed to an acid-base reaction. So when we do this, here's our new bond. I'll draw that in red. Here's the product where it adds to the acetaldehyde. Now you're actually stuck here because unlike our typical Aldol reaction, we don't have the base and water around. So what you would normally do is just add some dilute acid to protonate this. And because of the way this reaction works without having the hydroxide around, we can stop here and we can isolate this beta hydroxyketone. If you do want The alpha beta unsaturation, what you could do is just add some base, water, you might heat it up for good measure, and that will cause water to be lost. So now we get the alpha beta unsaturated ketone.